Okay, so let's go ahead and get through this first one. Haha. What kind of unit is this? What does this unit measure? Density. Are we okay with that? Because density is a measure of how much stuff I can get compacted into a particular volume. And so we've got tons and yards cubed. Who in the hell would need to use something that's tons and yards cubed?
Dump trucks with gravel.
Dump trucks with gravel. Gravel, they don't really care about what the density is. It's just rock. What'd you say?
Like big mining operations.
Big mining operations. So you think about those giant construction vehicles, not like the ones that they use in town, but the ones who use wheels when they're done with it. They turn into whole playground structures by themselves. They will pick up a bucket of dirt out of a mining operation area, and then they'll take that bucket of dirt and then they'll mass it out, and they'll figure it out what the density of that dirt is. Why?
Figure out what actual minerals and
If the dirt isn't very dense, what's not in there? Gold, platinum, silver, stuff that has metals that have higher densities. I mean, it's definitely not telling you exactly what's there, but it can tell you the approximate content. If they already know there's gold in the ground, then they can figure out based off of the density of just regular dirt, what percentage of the metal, what percentage of that dirt is actually gold. And so they can decide if it's worthwhile for them to mine that site or not. Okay, so I'm given 2.3, what was that about? Stop it. 2.34 tons per yard cubed. All right, so what do you want to get rid of first? Tons. Okay, so I gave you a unit conversion to go from pounds into kilograms, but we can go from tons into pounds and then into kilograms. So where do I put the ton unit to get it to cancel out with what I already have? All right, so I put tons down in the denominator, and I know, or I could have looked up a pound number here, and so it's 2,000 of these guys and one of those, and then the tons cancel out. Okay, and then I can use the unit that conversion that I gave you, that 2.2 pounds is equal to 1 kilogram, and cancel that out. And then I can say 1 kilogram is equal to how many grams? 1,000. Okay, so I took care of my my first unit. Now I need to get rid of the yard unit. This one's a slightly more complex. Why is it more complex? Yeah, I actually have to get rid of yard 3 times. So if I wanted to get rid of yard 1 time and turn it into, how many inches are in a yard?
36.
So yeah, 3 feet, 12 inches, 36. So let's go that route. So if I put why would I put the yard up here? Eliminate, so I got yards down here, I could cancel that out. If I did this unit conversion right here, what would happen? This yard would cancel what over here?
Only one of them.
Yeah, that 3 would become a 2. There'd still be 2 yards cubed, or there'd still be 2 yard units in the denominator, and I would need to do this again. Are we okay with that? That does 2 things for me. There are 3 yard units on top, so all 3 yard units get canceled out on the bottom, and it also gives me 3 inch units on the bottom, because I need to maintain the volume unit in the denominator. So inches times inches times inches would be inches cubed. Another way to do this, and a slightly faster way to do this, okay, so I need to get rid of yards cubed. So I'm going to put a cube right there. And that's perfectly acceptable mathematically if every other number and every other unit in this fraction is also cubed. So I'll put a 3 here, and a 3 here, and a 3 here. That's the exact same thing as I just had up there, right? Because what I had up there before in the numerator was 1 yard, and then 1 yard, and then 1 yard. And the denominator had 36 inches 3 times. Well, that's what that is, just in a condensed format. So then I can cancel out the yard cubed, and all those yards disappear. And now I've got inches cubed in the denominator. And I'll need to do the same kind of thing. I'll put inches cubed up here, and I'll put centimeters down here, cubed, and then 2.54 and 1 and 3 and 3. So everybody also gets cubed. And then the inches cubed get canceled out. So the units that I have remaining, the only ones that haven't been canceled, are grams and centimeters cubed. And times 2.23 divided by 2.2 divided by 36 cubed divided by 2.54 cubed. Miss anything? Oh, times 1,000. All right, I got 2.78. Is that an acceptable answer? Three significant figures in that 2.34 yards or tons per yard cubed. So then, yeah, 3 sig figs. Questions about that one? Okay. So we want to solve for temperature Fahrenheit. Multiply both sides by 9, divide both sides by 5. So 9/5, and then 9/5 over here. So I'll have temperature Celsius times 9 divided by 5, and that equals temperature Fahrenheit minus 32. So then I'll just add 32. No, 32. 32. And then add 32 over here. So I'll get temperature Fahrenheit is equal to temperature Celsius times 9 divided by 5 plus 32. All right. And then convert 100 degrees Fahrenheit into degrees Celsius. Before you start this problem, what should you expect? For your answer? I don't care about the decimal part.
Your Celsius number's gonna be smaller than Fahrenheit. Just
Okay.
Something to think about.
So, do you know about what the Celsius number is going to be? That's what I'm really asking.
Yeah, it's gonna be like about a third,
Can you give me a more,
closer to 38.
pretty close to 37, 38. How should you know that?
Because body temperature.
Because body temp's 37. So remember, I want you to remember 0 degrees Celsius, about 20 degrees Celsius, 37 degrees Celsius, and 100 degrees Celsius. Those are the important Celsius numbers to know. So if you see this number right here, and you come up with an answer of like 57 for some reason, like, okay, I did my math wrong, because my answer better be something really close to 37. Okay, so I want to convert the Fahrenheit. So 100 minus 32 times 5 divided by 9 equals my temperature Celsius. Is this okay to write my equation like this? It is not. Why?
Because it will multiply up to 5 minus 5, 32.
This 32 will be multiplied by 5, then divided by 9, and then subtracted off that 100. You'll get a wrong answer. So there needs to be a set of parentheses here. There don't need to be in this answer or this equation up here, because the order of operations is going to do the plus 32 last anyway, so it doesn't really matter. But that first one, or this one that we're doing right now, if you do not subtract off that 32, that's where your answer is going to be incorrect. And you can be sure on a multiple choice test, answer A is going to be whatever it is without the parentheses. So I've got 100 minus 32 times 5 divided by 9 equals, so it looks like 37.8. No, that's not enough. 37.78. That's better. Degrees Celsius. And then I'm going to add 273 to that. I'll get 0.78, 310. Okay? Is that right? That looks right. Except that's too many sig figs for this one. Technically, how many sig figs do I get for
4.
3. Why?
Oh.
Remember, we line the decimal places up, and whichever one has the least, wherever the least number of sig figs is, so I would chop everything off after that. So 311 actually would be the answer for that one. All right, I want to convert 290K into Celsius, so subtract off 273, I get 17 degrees Celsius. So if I've got 17 degrees Celsius, what temp Fahrenheit should I expect? What are the 4 Celsius numbers? I hope you know. Room temp is one of them, and that's somewhere around 20. So this should be like 65-ish, something that not too, maybe a little cold, but not too uncomfortable. All right, so degrees Celsius. I'm going to multiply this by 9, divide by 5, and then add 32 to it. So 17 times 9 divided by 5 plus 32 equals 62.6 degrees Fahrenheit. Since there's only 2 sig figs there, 63 degrees Fahrenheit. You good with that?
Question on the previous one, if the starting with 100.0 Fahrenheit and you kept 4 sig figs into the next,
Yeah, this guy here is 4 sig figs.
so you wouldn't go 310.8 for an answer?
You don't, because when you're using addition and subtraction, how do we determine the number of sig figs something gets? I've put all the numbers in, line their decimal places up, and whichever decimal, wherever one goes the least, I just put a line, and then I only keep stuff that was before that. So since there's no numbers here and here, then I don't know what these could be. So then the fact that this is 7, 8 doesn't mean anything, because this could be a 9 or a 1, and I don't really know. So then all of this stuff doesn't matter as far as my answer goes, but it will matter as far as rounding up, because I know for a fact that there's at least a 7 in that tenths place, right? So that 7 is forcing the round up to the 311. What do you guys have for this one?
Stuff comes in with 310.
Okay.
Tightly packed is,
I like tightly packed. I like how cramped the substance is, how tightly packed the substance is. That connotates basically what density is. All right, so I want to know if this thing floats. So I'm looking for density. So what are the units for density?
Grams per cubic centimeter.
All right, so a mass unit over a volume unit. So there's the unit that I'm looking for. I have 2 numbers. How would I orient them to give myself those 2 units the way they are? I'm just going to put 240 grams in a numerator and 268 centimeters cubed in a denominator, and I'm going to get those units in those particular places. So I get 240 divided by 268, so I get 0.895, and I have 2 sig figs here, so what do I do?
Cut it off and round.
Sorry, say again?
Cut it off and round.
Okay, so what do I end up, what's my actual answer going to be? 0.90, yep. So why do I need that second 0 there? It's telling me I was accurate to the hundredths place, so that stays. If I wasn't accurate to that, I just wouldn't write it at all. But this is telling the person that the real crux of the whole sig figs is this is a significant figure, this 0 here. So how sure are you about this 9?
Positive.
Positive. I am positive that that 9 is a 9 because that last number is significant. So usually the way it works with measurements is I'm looking at something and it'll say it's accurate to this plus or minus some amount. And so like on a graduated cylinder, it's gonna be, could be plus or minus 0.5 milliliters, could be plus or minus 0.05 milliliters. And then that person, if you give them that value, the tenths place or the hundredths place, they know the number in front of that is absolutely positive. They guessed on the last one, but on the first, this one right before that, they're sure about that. So you're gonna be doing that today in lab with these pennies, and there'll be graduated cylinder, and it's gonna go up to an area, and there's gonna be two lines, and it's gonna be kind of blurred, and you're gonna sort of guess in between how far it has gotten. But you're absolutely sure about the next number in, because the other one, you're pretty sure about, kind of sure about. Is this thing gonna float?
Yes.
Yeah, density less than 1. Okay, so what are we looking for in this next problem?
Final temperature.
I'm looking for a final temperature. So basically, I need a number that's got a temperature unit. And what I've been given here are calories, a temperature unit, and a grams value, and then I was told that it's glass. So then I can look up that the specific heat for this is 0.22 calories per gram degree C. So I'm looking for a number that's got Celsius. Since you generally aren't given the answer in a problem, this guy right here isn't the actual answer. So I need to use one of the values that I've been given that's got a degree Celsius unit in it, and then I can calculate out my answer. Tell me what's going on. Like, picture what the scenario is.
You're applying heat to just a flame to glass.
All right, so I've got 675 grams of glass. It's kind of like hanging there in the air. I flip a Bunsen burner on, and I send in 3,750 calories of energy into it. So what's going to happen to its temperature? It's going to go up. Okay. And I know what its initial temperature is. So when I'm going to do this calculation is to determine how much the temperature has gone up because I added 3,750 calories into it. So what I'm going to do is, I've got grams, I've got calories, and I've got this unit here. So I'm going to put grams times degrees C divided by 0.22 calories. Why did I do that? Because I need degrees C in the numerator, so my answer has units of degrees C. Is it okay to flip the specific heat value over? Is that okay? How about this? 1 foot is equal to 12 inches. Everybody's fine with that. How about 12 inches equal to 1 foot? Is that okay? So it doesn't matter. Once I have a fraction and that fraction is set, that is a property for specific heat. So if I put 0.22 calories into some glass and the thing is 1 gram big, it's going to raise its temp 1 degree Celsius. So it doesn't matter which one of those two things that I put in the numerator and which one I put in the denominator, as long as everything that was in the denominator, when I flip it over, goes up to the numerator and vice versa. So what I need to do now, I got the degree C where I want it, but I need to get rid of the grams and the calories. So what do I want to do?
What determined the 0.22 calorie number?
What determined it?
Yeah, how do you-
Some dude,
Oh.
probably. I say dude because that one's known for a long time, and women didn't do science back then, so I'm pretty sure it was some dude. So they just look it up in a book. So it was okay for me to do it on this homework assignment because I knew you could just flip open your notes or look it up online and see what the actual value was. On an exam, I can't do that because I'm not expecting you to memorize every substance's specific heat. So on an exam, it would have told you what the specific heat was. So a person has actually done this, like taken a chunk of glass, actually put 3,750 calories of heat into it, knew its initial temperature, knew its final temperature, and so then they worked the problem to figure out what its specific heat is. And I say a person did that, and that person probably did that like 500 times. And then they took all of those numbers and they published it in a peer-reviewed journal 150 years ago. And then that person, a bunch of people read that and was like, really? Okay, let's do it. And then they verified that experiment. So I need to get rid of grams and calories. What do you want to do? Okay, so I was given a gram value, and I'll toss the 675 grams in the denominator. That way my gram unit cancels out. Okay, great. Now what?
Put the calorie in there.
Okay, so I'm going to put 3,750 calories here and cancel that calorie out, and then I'm gonna get an answer that's got degrees C in it. Is it 25? I think it's 25. Let me make sure. 3750 divided by 675 divided by 0.22. Yeah, that's 25. And so I've got 265. Okay, so tell me about this. What is this? Am I done? Is that my answer? That's my temperature change. So that isn't my final temperature. What's my final temp?
Plus 15.
Plus 15. I started at 15 degrees. I threw an extra 25 degrees Celsius into this thing, so its final temperature is actually going to be 40 degrees Celsius. And is it okay for me to write it like that? It's not. What should I write?
Decimal.
I put a decimal after that 0. How come?
6 degrees.
That 0 and that 40 is significant. So I definitely need a decimal place there. What didn't I do with either of these two problems? These last two. What did I not use?
Equation.
I didn't use the equation. I never use any equations. I don't remember equations. I don't care about equations. I know the answers units. And then I take all the information that I have, shove it into this railroad track thing to give me the answers units that I want. That's all the formula does anyway. So if you looked at the formula and rearranged the formula, you'd see that you'd have calories in the numerator of the problem. You'd have grams in the specific heat in the denominator. It'd be the exact same thing, but I never bother memorizing any of those things because I don't need to, and I don't want you needing to, because those of you who are going into healthcare, there aren't equations to convert from drams into milliliters. There isn't an equation for it. There's just a unit conversion. And so if you know the unit conversion and you know the units that you're looking for, you just put things in the numerator and the denominator exactly how you want them and cancel stuff out until you get what you want left. That's it. No equation necessary. Okay, so I got a VW Bug and I got a pickup truck, and the pickup truck is twice as massive. So if they're moving at the same speed, that means we're talking about kinetic energy of this one thing is equal to kinetic energy of this other thing. They're not actually equal to each other. We're just comparing these two things. So it's 1/2 mv squared and 1/2 mv squared. All right, so what do I know? What can I do with this equation when I'm comparing these two things?
Cancel.
I can start canceling stuff. So I can get rid of the half right away because the half's in both of them. What else can I get rid of? The velocity squared can disappear because the velocity of both of these two things is the exact same thing. What's the factor difference between the two masses? The truck is double the mass, right? So how much more kinetic energy does the truck have? Twice as much. That's it. Twice as much kinetic energy. So let's do this again down here. So I've got 1/2 mv squared and 1/2 mv squared. So we'll do the same thing. Since the half is there, we'll cancel both of those out. Now I can't cancel either of the masses or the volume or velocities out. I still have a 2 for my truck. So the truck is twice as massive, so I'll have twice as much kinetic energy. But what's going on with the Bug? This guy, the velocity here is squared. Sorry, it's doubled. But since the velocity has an exponent associated with it, what does that 2 turn into? A 4. So the Bug's total compared velocity is 4 times that of the truck in terms of kinetic energy. But the truck is still twice as massive. So who's got more kinetic energy?
The Bug,
The Bug definitely does, but by how much?
factor of 2.
Only a factor of 2. So this was 2 times bigger over here, but this is 4 times bigger over here. So then that means the Bug over here is actually twice the kinetic energy. So do you want to get hit by this big pickup truck at 30 or this VW Bug at 60? Pickup. Sadly. Neither. Probably the best answer, right? No, thank you. Calorie definition?
Unit of measured heat.
Okay, more than that though.
How much heat it takes to heat 1 gram of water, 1 degree Celsius?
Is that a lot of heat?
No.
No. 1 gram of water, 20 drops, 1 degree Celsius? No, not very much heat. Okay.